and good afternoon everyone. Today I will discuss about the fundamental of electrochemistry. But first of all, what is the electrochemistry? Electrochemistry is the branch of chemistry that studies the relationship between chemical reaction and electrical energy and explore how chemical reaction can generate electricity and how electrical energy can be used to drive chemical reaction. Imagine a simple battery like the one used in a flashlight. This battery is a prime example of electrochemistry in action. Let's proceed to the three concepts of its fundamentals. We have reduction reaction, electrochemical cell, and electrolyze. So let's proceed to the reduction reaction. It's a chemical reaction in which electrons are transferred between two reactants participating in it. Imagine, when magnesium combined with oxygen to form magnesium oxide, electrons on the magnesium atoms are more strongly attractive to the oxygen atom than they are to their own nucleus, so they swap over. Creating two ions, the magnesium ions have electrical charge of positive 2 because they've lost the electron, and the oxide ions have a charge of negative 2 because they gain 2 electrons. Positive and negative charge attract to the ions, bond to form allytons. This is magnesium oxide, a white powder. Oxidation is the loss of electron, so if this reaction, the magnesium has been oxidized. So remember, oxidation and reduction are really just different aspects of the same things. So we can mix the word together and call the combination redox that involves the transfer of electron. So I can remember which reactants are oxidized and which are reduced. Using the mineralogy oilage, oxidation is lost and reduction is gained, and that is oilage. Let's proceed to the electrochemical cell. What is electrochemical cell? Electrochemical cell is the device that can generate electrical energy from the chemical reaction occurring in it or use the electrical supply to it to facilitate chemical reaction. These devices are capable of converting chemical energy into electrical energy or vice versa. The example is 1.5 volt cell, which is used to power many electrical appliances such as TV remote and clocks. And now, let's proceed to the electrolyze. Electrolyze is a substance that is dissolved in water into charged particles called ion. The positively ion are called cation and the negative ions are called anion. And how they work? When sodium chloride dissolved in water, it split or dissociates into a positive sodium ion and a negative chloride ion in addition to our hydrogen and hydroxide ion from the water, and that is called electrolyze. And this is the 5 conductors, materials that allow electricity to flow to them easily. The silver, gold, copper, steel, and seawater. It is the property of conductors that allow them to conduct electricity.
The next will be the types of electrochemical cell. What is galvanic cells or voltaic cells? The electrochemical cells that produce electrical energy with the use of chemical energy are called voltaic cells. These are also known as galvanic cells. Among other cells, a galvanic cell is a type of electrochemical cell. It is used to supply electric current by making the transfer of electrons through a redox reaction. A galvanic cell is an exemplary idea of how energy can be harnessed using simple reactions between a few given elements. This is the voltaic cell diagram. Spontaneous redox reaction. Let us understand how a voltaic or galvanic cell is created. In oxidation redox reactions, electrons are moved from one species to another species. Energy is released if the reaction occurs spontaneously. Therefore, the released energy is used to do useful work. To tackle this energy, It is required to the split reaction into two separate half reaction V's, oxidation and reduction. With the help of two different containers and wire, the reaction are put into them to drive the electrons from one end to the other end. This creates a voltaic cell. The principle of galvanic cell. Electric work done by a galvanic cell is mainly due to the Gibbs energy of a spontaneous redox reaction in the voltaic cell. It generally consists of two half cells and a salt bridge. Each half cell further consists of a metallic electrode dipped into an electrolyte. These two half cells are connected to a voltmeter and a switch externally with the help of the metallic wires. In some cases, when both electrodes are dipped in the same electrolyte, a salt bridge is not required. Let's proceed in electrolytic cells. These involve non-spontaneous reactions and require an external electron source like a DC battery or an AC power source. Electrolytic cell, any device in which electrical energy is converted to chemical energy or vice versa. Such a cell typically consists of two metallic or electronic conductors, electrodes held apart from each other and in contact with an electrolyte, usually a dissolved or fused ionic compound. A comparison between galvanic cells and electrolytic cells. Galvanic cell converts chemical energy into electrical energy. Electrolytic cell converts electrical energy into chemical energy. Galvanic cell contain negatively charged anodes and positively charged cathodes. Electrolytic cell contain positively charged anode and negatively charged cathode. Galvanic cell feature spontaneous cell reactions. Electrolytic cell feature non-spontaneous cell reactions. Diagram and working of an electrolytic cell. Molten sodium chloride can be subjected to electrolysis with the help of an electrolytic cell, as illustrated below. Here, the two inert electrodes are dipped into molten sodium chloride, which contains dissociated sodium plus cations and chloride minus anions. When an electric current is passed into the circuit, the cathode becomes rich in electrons and develop a negative charge. The positively charged sodium cations are now attracted towards the negatively charged cathode. This results in the formation of metallic sodium at the cathode. Simultaneously, the chlorine atoms are attracted to the positively charged cathode. This results in the formation of chlorine gas at the anode, which is accompanied by the liberation of two electrons, finishing the circuit. The associated chemical equations and the overall cell reaction are provided below. Reaction at cathode. A reduction reaction where the sodium ion gains an electron and is reduced to a sodium atom. Reaction at anode. 2 units of a negatively charged chlorine anion in a chemical equation and is a diatomic molecule with the release of 2 electrons. Cell reaction. 2 sodium atoms combine with 1 diatomic chlorine molecule to form 2 ionic units of sodium chloride. Thus, molten sodium chloride can be subjected to electrolysis in an electrolytic cell to generate metallic sodium and chlorine gas as the product. Fuel cells. An electrochemical cell that generates electrical energy from fuel via electrochemical reaction. Fuel cells directly convert the chemical energy in hydrogen to electricity, with pure water and potentially use heat as the only byproducts. Hydrogen-powered fuel cells are not only pollution-free, but they can also have more than 2 times the efficiency of traditional combustion technologies. Fuel cells can provide heat and electricity for buildings and electrical power for vehicles and electronic devices. How fuel cells work? Fuel cells work like batteries, but they do not run down or need recharging. They produce electricity and heat as long as fuel is supplied. A fuel cell consists of 2 electrodes, a negative electrode or anode and a positive electrode or cathode, sandwiched around an electrolyte. A fuel, such as hydrogen, is fed to the anode, and air is fed to the cathode. In a polymer electrolyte membrane fuel cell, a catalyst separates hydrogen atoms into protons and electrons, which take different paths to the cathode. The electron go through an external circuit, creating a flow of electricity. Batteries, energy source consisting of one or more electrochemical cells, a device that converts chemical energy into electrical energy by using electrodes and an electrolyte. There are 3 different types of batteries that are commonly used: alkaline, nickel metal hydride, and lithium ion. The use of different metals and electrolytes in these batteries gives them different properties, which means they are suited to different contexts. Examples of secondary batteries include nickel-cadmium, lead-acid, and lithium-ion batteries. Fuel cells are similar to batteries in that they generate an electrical current, but require continuous addition of fuel and oxidizer.
Application of electrochemical energy. There are 3 aspects of electrochemical energy: the portable electronic devices, electric vehicles, and renewable energy storage. First, let's talk about portable electronic devices. What is portable electronic devices, or PED? Any piece of lightweight electrically powered equipment. Those devices are typically consumer electronic devices capable of communication, data processing, and computing. And more info about PED, or portable electronic devices. The term portable electronic devices encompasses a broad spectrum devices, making a precise definition challenging. However, there are 4 common characteristics emerge. And the 4 common characteristics emerge: the portability, electrofunctionality, battery powered, and data storage and processing. First, let's talk about portability. Portability, those devices are designed to be easily carried and used in various locations. For example, a portability is a power bank. Second, electronic functionality. They rely on electric circuits and components to perform their task. Third, battery powered. Most portable devices operates on batteries, allowing for independent uses. And lastly, data storage and processing. They often have the capability to storage, process, and transmit data. Second application of electrochemical energy is the electric vehicles. What is electric vehicles? An electric vehicles, or EV, is a vehicle that uses one or more electric motors for propulsion. The device can be powered by a collector system with electricity from extravehicular sources, or can be powered autonomously by a battery or by converting fuel to electricity using a generator or fuel cells. Use are electric motors that is powered by a fuel cells or battery. And there are some benefits of electric vehicles. The first benefit of electric vehicles is the environmental sustainability. EVs produce zero tailpipes emission, significantly reducing air pollution and greenhouse gases emission. This is especially important in urban areas where air quality is often poor. Next is the energy efficient. EVs convert higher percentage of energy into motion compared to gasoline engines, resulting in greater fuels. And last, quiet operation. EVs are significantly quieter than gasoline vehicles, reducing noise pollution and creating a more pleasant driving experience. If there are some benefits in electric vehicles, and there are some challenges too. The first challenge in electric vehicles is battery cost. The cost of electric vehicles batteries is still relatively high, contributing to higher upfront cost of EVs compared to gasoline vehicles. Next is the battery life. Electric vehicles battery life have a limited lifespan and eventually need to be replaced, which can be expensive. And the last is range anxiety. The limit range of most EVs or electric vehicles compared to gasoline vehicles can be a concern for drivers, especially on long trips. And the last application of electrochemical energy is the renewable energy storage. What is renewable energy storage? Energy storage is a technology that holds energy at one time so it can be used at another time. Building more energy storage allows renewable energy sources like wind and solar to power more of our electric grid. And there are some types of renewable energy storage. And I have 3 examples of renewable energy storage are pump hydroelectric storage, flywheel storage, and hydro energy storage. First, let's talk about pump hydroelectric storage. This established technology involves pumping water to a higher elevation during periods of low demands, using access to renewable energy when electricity is needed. The stored water is released to generate electricity through turbines. While effective, it requires specific geographic condition and can have environmental impacts. Second, flywheel storage. Flywheel storage kinetic energy by spinning a rotor at high speeds. When energy is needed, the rotor's speed decreases, converting the stored kinetic energy into electricity. Flywheels offers the faster span time and are often used to short-term power quality and reliability services. Last is the hydro energy storage. Access renewable electricity can be used to split water into hydrogen and oxygen through electrolysis. By the hydrogen can then be stored and used to generate electricity via fuel cell or combustion when needed. Hydrogen is also being explored for its potential in long-term and large-scale storage.
Introduction to nuclear chemistry. Overview of nuclear chemistry. Nuclear chemistry is the study of how atomic nuclei can change into new nuclei. The atomic itself is changing in nuclear reactions. As with the conventional chemical reactions, a nuclear reaction is accompanied by energy changes. The energies within the nuclei of atoms are hundreds of thousand times larger than the energies of chemical bonds. In order to balance nuclear reactions, one must focus on subatomic particles within the atom: protons, neutrons, and electrons. Nuclear processes have their own unique classification as well. We will study many of the more fundamental nuclear reactions in this chapter.
Let's talk about the structure of nucleus. So first, what is nucleus? The nucleus is the control center of eukaryotic cell, housing the cell's genetic material and DNA. It's a complex and dynamic organelle with several distinct structures that work together to ensure the proper functioning of the cell. So how about the structure of the nucleus? I'm gonna share 5 structure of the nucleus. There are nuclear envelope, chromatin, nucleolus, nuclear plasm, and the nuclear matrix. Let's talk about nuclear envelope. Nuclear envelope is a double membrane that surrounds the nucleus, separating it from the cytoplasm. It's like a fortress protecting the cell's precious DNA. The envelope consists 2 distinct lipid bilayer membranes, each with its own unique composition and functions. The outer membrane is continuous with the endoplasmic reticulum and is stubbed with ribosomes. The inner membrane is associated with nuclear lamina and helps maintain the shape of the nucleus. The nuclear envelope isn't a solid barrier. It's stubbed with nuclear pores, complex structures that acts as gateways, allowing selective passage of molecules between the nucleus and cytoplasm. These pores are essential for transporting essential materials like RNA and proteins in and out the nucleus. The space between the 2 membranes is called perinuclear space. It's continuous with the ER lumen. The second structure is chromatin. So what is chromatin? Chromatin is the complex of a DNA and proteins that makes up chromosomes. It's a highly organized and dynamic structure that helps to package and organize DNA, preventing it from becoming a tangled mess. Imagine DNA as long, tangled string. Chromatin helps to neatly package and organize this string, preventing it from becoming a tangled mess. This packaging is essential for efficient DNA replication and transcription. The primary protein components of chromatin are histones, highly basic proteins that associate readily with DNA. Histones combined with DNA form nucleosomes and the subunit of chromatin. A nucleosome describes a segment of DNA associated with 8 histone proteins. Chromatin can exist as euchromatin or heterochromatin. Euchromatin is the form of chromatin present during gene expression, and it has the characteristic beads on a string appearance. It's activated by acetylation. In contrast, heterochromatin is the inactive form and it's densely packed. On electron microscopy, euchromatin stains are lighter than heterochromatin, reflecting their relative densities. The third is nucleolus. So what is nucleolus? Nucleolus is a prominent, dense region within the nucleus. It's not membrane bound, but it plays a crucial role in protein synthesis. The nucleolus is the site of ribosome assembly. Ribosomes are the circular machinery that translate RNA into proteins, the building blocks of life. The nucleolus also plays a role in synthesizing ribosomal RNA, a key component of ribosomes. The nucleolus forms around the tandems repeat of rDNA, DNA coding for ribosomal RNA. These regions are called nucleolar organizer regions. The fourth part is nucleoplasm. So what is nucleoplasm? Nucleoplasm is the jelly-like substance that fills the nucleus. It's a complex mixture of water, ions, enzymes, and other molecules that provides the nucleus with its internal environment. Nucleoplasm provides support for the nucleus and its components, keeping everything in place. It acts as medium for various metabolic processes, including DNA. The fifth is nuclear matrix. Nuclear matrix is a network of protein fibers that provide structural support for the nucleus and helps to organize its contents. It's like a scaffolding that helps to keep everything in place. The nuclear matrix provides anchoring points for chromatin, nuclear pores, and other nuclear structures. The nuclear matrix is involved in DNA replication and transcription, providing a framework for these processes. What is the nucleus in vital role? The nucleus is a marvel of cellular organization, a dynamic and essential structure that governs the life of eukaryotic cells. It plays a central role in genetic information storage, replication, and expression. Understanding the nucleus is crucial for comprehending the fundamental processes of life and intricate working of our cells. Composition of the nucleus. The nucleus of an atom consists of a tightly packed arrangement of protons and neutrons. Of the two, the proton possess a net positive charge and hence the nucleus of an atom is positively charged on the whole, and the negatively charged electrons revolve around the central nucleus. Since the mass concentration at the nucleus of an atom is immense, the nuclear forces holding the protons and the neutrons together are also large. The protons are in such close vicinity to each other inside the tiny nucleus, and therefore the electrostatic forces of repulsion also act inside the nucleus. Nuclear energy relies on nothing but releasing the energy trapped in the nucleus of an atom. The total number of protons in a nucleus is equal to the number of electrons revolving around the nucleus and hence the atom, on the whole, is electrically neutral.
The next topic under the nuclear chemistry is the radioactive decay. Now, what is radioactive decay? Radioactive decay is a natural, spontaneous process by which an unstable atomic nucleus loses energy by emitting radiation. The transformation of radioactive decay leads to the conversion of the original nucleus into a different nucleus, which may be of a different element, is a different isotope of the same element. Now, what are the types of the radioactive decay? These are the types of radioactive decay: the alpha decay, the beta decay, and the gamma decay. Now, let us talk about first the alpha decay. Now, what is alpha decay? Alpha decay is a nuclear decay process by which the parent nucleus emits an alpha particle. The alpha particle is structurally equivalent to the nucleus of a helium atom. The process of an alpha decay is the nucleus emits an alpha particle in which consists of 2 protons and 2 neutrons. As you can see on the screen, this is an example of an alpha decay. Uranium-238 to thorium-234. This decay occurs in the uranium-238 nucleus that decays into thorium-234 nucleus. This explains that alpha particle has a relatively large mass, positive electric charge, and poor radiation penetration. The next type of a radioactive decay is the beta decay. Beta decay is a type of radioactive decay that converts to a proton to a neutron or vice versa. It is also the process of the nucleus emits a beta particle, either an electron or a positron. Now, there are 2 kinds of beta decay: the beta plus decay and the B minus decay. Let's talk about first the beta plus decay. What is beta plus decay? Beta plus decay is a process of proton transforms into a neutron while emitting a positron and a neutrino. Example that provided on the screen is a beta plus decay. Beta plus decay involves the weak force causing a proton to change into a neutron. This process releases a positron and an electron neutrino, and it also reduces an element atomic number by 1, turning it into a different element. As a result, carbon-10 decays to boron-10. Next is the beta minus decay. What is beta minus decay? A beta minus decay is a process of neutron in the nucleus transforms into a proton while emitting an electron and anti-neutrino. The example provided in the beta minus decay explains that both carbon-14 and nitrogen-14 have 14 nucleons protons and neutrons. Carbon-14 has 6 protons and 8 neutrons, while nitrogen-14 has 7 protons and 7 neutrons. One of the neutrons decayed into a proton. This means that carbon-14 underwent beta-minus decay. The next type of radioactive decay is the gamma decay. Gamma decay is the process of nucleus releases excess energy in the form of gamma rays or high energy photons without changing its number of protons and neutrons. Effects of gamma decay often accompanies other types of decay as the nucleus transition from a higher to a lower energy state. Next is a decay equation. Decay equation describes how the amount of radioactive substance decreases over time as a result of decay. Now, let's see how this applies to each type of decay. First is an alpha decay. In alpha decay, the nucleus of an unstable atom emits an alpha particle which consists of 2 protons and 2 neutrons. The emission of an alpha particle reduces the atomic mass by 4 units and the atomic number by 2 units. Example is a uranium-238 decays to thorium-234 by emitting an alpha particle. This explains that the half-life of uranium-238. Using the decay equation, we can calculate how much uranium-238 remains after a given period of time by substituting the appropriate values. Next is a beta decay. Beta decay, a neutron inside the nucleus is converted into a proton and electron called a beta particle. Example for this is the carbon-14 decays into nitrogen-14. This explains that carbon-14, commonly used in carbon dating, has a half-life of about 5,730 years. By applying the decay equation, we can calculate how much carbon-14 remains in an archaeological sample after a certain period. Next is the gamma decay. Gamma decay occurs when an excited nucleus releases excess energy by emitting a gamma ray or a high-energy electromagnetic radiation. Gamma rays do not carry charge or mass, so they do not change the atomic number or mass of the nucleus. Instead, the nucleus transitions from a higher energy state to a lower energy state. Example reaction is the cobalt-60 emits a gamma ray to transition to a lower energy state. In gamma decay, the parent nucleus typically undergoes alpha or a beta decay first and then emits a gamma ray. The decay equation still applies to the initial transformation. Once the excited nucleus is in the stable state, gamma decay occurs rapidly. The gamma emission doesn't change the quantity of nuclei, but rather the energy state of the nucleus. Now, how the half-life connects to all types of decay. For all the 3 types of radioactive decay, half-life is the key concept. The half-life is the time it takes or half of the radioactive nuclei to decay, regardless of the decay type, the alpha, the beta, or the gamma. Next topic that in line to a radioactive decay is the radioactive series. Radioactive series is a sequence of successive radioactive decays that certain unstable isotopes undergo until they form a stable nucleus. Starting from a parent isotope, the series progresses through multiple decay steps, producing intermediate isotopes, eventually ending with the stable daughter isotopes, just like the example that I mentioned earlier in the alpha decay. In line with the radioactive decay series is the parent isotopes. What is parent isotopes? A parent isotope is the original unstable radioactive isotope that undergoes decay in a radioactive process. The parent isotope transforms into a daughter isotope which may be stable or may further decay if it's still radioactive. One of the examples that I mentioned earlier is the uranium-238 is the parent isotope in its decay series, eventually becoming lead-206. Now let's proceed to daughter isotopes. What is daughter isotopes? Daughter isotopes are the products formed from the radioactive decay of a parent isotope. When a parent isotope undergoes decay, such as alpha, beta, gamma decay, it transforms into a new isotope called the daughter isotope. The daughter isotope can be either stable or radioactive. If radioactive, it may continue decaying until a stable isotope is formed. For example, in the decay of uranium-238, The daughter isotope is thorium-234. This process can continue through several generations in a decay series until a stable isotope like lead-206 is formed.
Nuclear reactions. In nuclear physics and nuclear chemistry, a nuclear reaction is a process in which two nuclei or a nucleus and an external subatomic particle collide to produce one or more new nuclides. Thus, a nuclear reaction must cause a transformation of at least one nuclide to another. If a nucleus interacts with another nucleus or particle, they then separate without changing the nature of any nuclide. The process is simply referred to as a type of nuclear scattering rather than a nuclear reaction. In principle, a reaction can involve more than two particles colliding. But because the probability of three or more nuclei to meet at the same time and at the same place is much less than for two nuclei, such an event is exceptionally rare. The term nuclear reaction may refer either to change in a nuclide induced by collision with another particle or a spontaneous change of a nuclide without collision. Natural nuclear reactions occur in the interaction between cosmic rays and matter, and nuclear reaction can be employed artificially to obtain nuclear energy at an adjustable rate on demand. Nuclear chain reaction in fissionable materials produce induced nuclear fission, whereas nuclear fusion reaction of light elements power the energy production of the sun and stars. Nuclear fission. Nuclear fission refers to the splitting of an atomic nucleus into two or lighter nuclei. This process can occur through a nuclear reaction or through radioactive decay. Nuclear fission reactions often release a large amount of energy, which is accompanied by the emission of neutrons and gamma rays. Nuclear fusion. In nuclear fusion reactions, at least two atomic nuclei combine or fuse into a single nucleus. Subatomic particles such as neutrons or protons are also formed as products in these nuclear reactions. An illustration of the nuclear fusion reaction between deuterium and tritium that yields helium and a neutron is provided above. Such fusion reactions occur at the core of the sun and other stars. The fusion of deuterium and tritium nuclei is accompanied by a loss of approximately 0.0188 mu of mass. Approximately 1.69 multiplied by 10 to the 9th kilojoules of energy are generated for every mole of helium formed. So what's the difference between nuclear fission and nuclear fusion? Nuclear fission, a heavy nucleus breaks up to form two lighter nuclei, while nuclear fusion, two light nuclei combine to form a heavy nucleus. Nuclear fission, it involves a chain reaction while nuclear fusion, chain reaction is not involved. Nuclear fission, the heavy nucleus is bombarded with neutrons, while nuclear fusion, light nuclei are heated to an extremely high temperature, etc. So let's proceed to our next topic, energy released in nuclear reactions. Nuclear energy is the energy held in the nucleus of an atom. It can be contained through two types of reactions, nuclear fission and fusion. Nuclear fission produces energy through the splitting of atoms, which releases heat energy that can generate steam and then be used to turn a turbine to produce electricity. All of today's nuclear plants use fission to generate electricity. The fuel most commonly used for fission is uranium, although additional elements such as plutonium or thorium can be used. Nuclear fusion is a nuclear reaction in which two or more atomic nuclei collide at a very high speeds and join to form a new type of atomic nucleus. During this process, matter is not conserved because some of the matter of fusing nuclei is converted into photons, which produces usable energy. This process is what allows the sun and stars to give off energy. Fusion power offers the prospect of an almost inexhaustible source of energy for future generations. However, creating the condition of nuclear fusion presents a potentially insurmountable scientific and engineering challenge. A recent experiment has shown that nuclear fusion can be achieved, however, it has not yet been successfully demonstrated on a commercial scale.
And now, let's proceed to the basic principle of nuclear reactors. The number one is nuclear chain reaction. Nuclear chain reaction within the reactor produces heat, which is transferred to a coolant, most commonly light water. And the next one is the coolant. Coolant is make the water stem directly to another loop of water and to the steam. And the last is the turbine. After the coolant steam the water, it passes to a turbine which is spin a generator and turbine produce an electricity. And now, let's proceed to the control of nuclear reactor. We have 5 control of the nuclear reactor: the cure, containment, cooling tower, and coolant. The first one is the cure. The cure is where the nuclear fission reaction takes place. It houses the nuclear fuel. They typically uranium in the form of fuel rods. And the next one is the turbine. The turbine is connected to a generator which converts mechanical energy into electricity. And the next one is the containment. The containment structure is a robust shield building that houses the steam turbine and generator. Containment designed to prevent the release of radioactive materials in the event of an accident. And the next one is the cooling tower. Cooling towers are tall structures that release excess heat from the reactor system into the atmosphere. And lastly, the coolant. The coolant is a fluid, usually water, that circulates through the reactor here to absorb the heat generated by fission. Different reactor designs use different coolant, such as pressurized water, boiling water, or liquid metal. The coolant plays a crucial role in preventing overheating and potential meltdowns. These 5 controls of nuclear reactor are important, work together in a complex system to safely and efficiently generate electricity from nuclear reactor fission. Each component plays a vital role in controlling nuclear reactor and managing heat and ensuring safety of the reactor at the environment. And now, let's proceed to the safety consideration and challenges. Multiplicity of barriers. This prevents the release of radioactive substance into the environment. The barriers include the fuel clothing, the reactor vessel, and the containment building. The next one is defense in depth. This strategy involves several protective layers between the source of radiation and the outside environment, aimed at preventing the escalation of accident. The next one is redundancy and diversity. Reactors are equipped with multiple diverse systems to perform essential safety functions. This means if one system fails, another can take its place, reducing the risk of accident. And lastly, strict operating procedure and trained personnel. Operators of nuclear facilities undergo regular training and must adhere to strict operating procedures to minimize human error.
Now, let's proceed to the next topic, which is the nuclear waste and disposal. What is nuclear waste and disposal? Nuclear waste is the byproduct of nuclear reactions such as those occurring in nuclear reactors or from the processing of nuclear materials. It includes radioactive materials that remain hazardous of 1,000 years. Nuclear waste disposal refers to the methods used to safely store or contain this waste to prevent radiation exposure to human and environment. These are the types of nuclear waste. First is the low-level waste, or the LLW. Next is the transuranic waste, or the TRU. Last is the high-level waste or the HLW. First, let us first discuss what is low-level waste. First type of the nuclear waste is the low-level waste. Low-level waste contains low amounts of radioactivity that includes items like contaminated clothing, tools, and medical equipment. It disposed of through shallows, burial, and incineration. Next would be the transuranic waste or the TRW. This type of nuclear waste contains elements heavier than uranium, typically from nuclear weapons production. This requires deep geological disposal. And lastly, high-level waste. This high-level waste type of nuclear waste is highly radioactive and generates heat, mainly spent nuclear fuel or waste from reprocessing. This requires cooling and long-term storage in deep and geological repositories. Now, after we discuss the three types of nuclear waste, here are some challenges and methods in nuclear waste disposal. One of the challenges in nuclear waste and disposal is a long-term radioactivity. Long-term radioactivity is a high-level waste remains radioactive for thousands to millions of years. This requires storage solutions that last for a long period without degradation. Next will be the environmental and health risk. This environmental and health risk, improper disposal can lead to contamination of soil, water, and ecosystem that posing serious health risk to humans and wildlife. Next will be the storage safety. Storage safety ensuring that waste containers and storage sites can withstand natural disasters like earthquake, floods, and other potential disasters. Next will be the public opposition. Public opposition concerns about the safety and environmental impacts lead to the resistance against building a new disposal sites. Next will be the cost. The cost of the constructions and maintenance and monitoring of secure waste repositories are so expensive, and these costs extended over long time frames. Last is the international cooperation. International cooperation in some countries may lack the infrastructure or resources to manage their nuclear waste, necessitating international agreements for safe handling and disposal. Now, let's talk about the environmental and safety concerns in nuclear waste and disposal. Nuclear waste possesses significant environmental and safety concerns due to its long-lasting radioactivity. Improper disposal can lead to groundwater contamination and harmful radiation exposure, threatening human health and ecosystems. Safe storage requires secure, long-term containment, and geological repositories, but risk includes potential risk, accidents, and the difficulty of maintaining oversight for thousands of years. Managing nuclear waste effectively remains a critical challenge for reducing environmental hazards and ensuring public safety.
And that's the video presentation of Group 1. And I hope you learned something. Thank you.